Detectable precedence is a filtering for the disjunctive constraint in which we will update the earliest start time of a set of activities. Let's consider this example. If you study the activity C and the activity A, and you try to put A after the activity C, okay, the best you can do is this way. But as you can see, there is an overlap. It means that it's impossible to schedule A after the activity C, given the two time windows that they have. And for the same reason, B can also not be scheduled after the activity C. That's impossible. And therefore, both A and B must be scheduled before the activity C. This is what we denote with this notation. A and B must both be scheduled before the start of the activity C. So if we take the earliest start time of the activities A and B, this is what we get, okay? And since we have deduced that A and B must be scheduled before the activity C, we will be able to prune in the start time domain of the activity C, we will be able to remove 8 and 9. And we will update and we will say that C cannot start before the time 10. The goal is to do this exactly the same filtering as we did there for the 3 activities, but for an arbitrary number of activities, all with the specific time windows, and we should do it as efficiently as possible. So a first definition that we need is how to decide that one activity is a precedence of another activity. It's a necessary precedence. And we will say that it's a detectable precedence in that case. So it's the same. So if the pink activity there, okay, you take the earliest completion time of this activity. If it is larger than the latest start time of this activity, of this quantity, it means that you must have a precedence that J must start before the activity I, okay? And we can denote by detectable precedence of I the set of all the activities that satisfy this property, okay? That are all the activities that must be scheduled before the activity I. All the activity J that must be scheduled before the activity I, because you have detected that it is impossible to schedule them after. And out of that set, you remove, by definition, the activity I itself, right? Because it might be the case that this is included. And then the filtering rule, once you have this set that is available to you, the filtering rule that you can apply is that the earliest start time of the activity I cannot be earlier than the earliest completion time of this detectable precedence set. And you can do that for all the activities I in your resource. In order to have efficient filtering algorithm for the detectable precedence rule that we just have seen, we should also be able to define nested sets. And the goal here is to see if there is a possible nested relations between the detectable precedence sets. In our definition, the activity I cannot be included in the set of detectable precedence of I, otherwise the filtering rule would not be valid, right? But if we would include the activity, so we do not specify that the activity I is excluded from this detectable precedence set, then there is a chance that we have a nested relations. And the relation between this detectable precedence prime notation and the previous one is this one, okay? The previous one is the new one out of which you might have to remove the activity I, okay? The goal now is to see in what order should we consider the activity I in order to have nested sets. It's quite easy to visualize on this picture which order we should choose. So what I have represented on these slides is my set of activities that are sorted here according to the earliest completion time of the activities. So EST of I, earliest start time plus the processing time, is the earliest completion time of each activity individually. We sort them like this, okay? And since we have sorted them like this, it's quite clear, now it's quite obvious that the detectable precedence set of the activity 1 is composed of the activity A here, right? And if you progress like that, then you take the next one, you can only add more activities in these detectable precedence sets of the activities. So once you are at the end of the earliest completion time of activity 2, you have now B added B and C, so 2 more in them. But the sets are nested, and so on. So if you continue like that, then you include the activity D. Okay? So that's the specific order that we should consider. Okay? That's also the earliest completion time of I. If we consider that order increasingly, then we will have nested relations for the detectable precedence prime sets. Okay? So if the activities again are sorted according to this criteria, then the detectable precedence sets are really in the nested relations as indicated there. This is exactly what we are looking for in order to design a very efficient filtering algorithm taking advantage of the theta trees. That's the pseudocode. So I will first sort the activities increasingly according to the earliest start time plus the processing time. Okay. So if I give you this one, this order, according to the earliest completion time, if you sort them like this, and that's another sorting, because as you can see, if you sort these ones like this, with a kind of double loop, you will be able to find the nested sets incrementally. So I first initialize my theta tree. It's an empty set, right? That's the empty set of activities. And then I will iterate according to the earliest completion time of the activities. Okay. So if I represent this loop, that's this order that you have there. Okay. And this loop there will iterate according to another order that is the one of the latest start time. Okay. And that is this order. So you iterate first in the external loop, you iterate according to the earliest completion time, so that order. And then for each activity I, you will include one by one the one that should be included in the theta tree, right? This is what you do there, okay? You consider them one by one according to the iterator that is given there, and the iterator is iterating in that order, the latest start time, which is this one. And so you can include them one by one in the theta tree. Once you have detected, for instance, for that one, that you have included the 3 of them, okay? Once you have done, you have included all the ones that are in the detectable precedence set of the activity I, okay? And so that's the theta tree. This is what the theta tree contains, is the detectable precedence set of the activity I. And now you can update the earliest start time of the activity I. But don't forget that the detectable precedence set prime, okay, is the one in which you possibly have the activity I itself. And the filtering rule should not include the activity I itself. Therefore, we should have the earliest completion time of all the activities inserted so far, but we should remove the activity I from this computation. And removing an activity from the theta tree is very simple. You just remove it, that's log n time, and then you can just reinsert it afterward. Okay? So let's consider the total time complexity of this algorithm. So that's n log n because you have the 2 sorting initially. You initialize the theta tree, that's also n log n because you need to sort them according to the earliest start time for the leaf nodes of the theta trees. And then you will insert them one by one. Each insertion will take log n time. And since you will have, in the worst case, because this algorithm is converging and eventually considering each activity exactly once, you will have exactly n insertions in the worst case, and so that's n log n also for this main loop. And so overall, the total time complexity is n log n. Let's see on our example how it works. So first you do the sorting of the activities, right? And so once you have sorted them, this is what I have represented there, okay? And if you have sorted them for the second sorting criteria, that's this one. And so the sorting according to the latest completion, to the earliest completion time, okay, is this one. And so the order is ABC. And coincidentally, that's also ABC for the sorting according to the latest start time. Okay, but that's pure chance. It shouldn't always be the case that you will have exactly the same order, of course. So we start by the initialization of the theta tree. So I represent the activities in gray to make sure that you see that the theta tree is empty. Okay, so we have the 3 activities in the theta trees, but we put -infinity for the earliest completion time and 0 for the processing time to make sure that they do not impact the earliest completion time at the root node as well. Then we iterate over the activities according to the earliest completion time, and so that's this order. So the first one that we will consider is activity A. So we take the activity A there, okay, right? And we see which one should we add inside the theta tree, considering the while loop. And you see that there are none of them, right? There are none of them that at the latest would start before the earliest completion time of activity A. So there is nothing to insert there. So we go to the next one, that's B. And again, we see that there is nothing to add in the theta tree. It becomes a little bit more interesting when you insert the activity C. Okay, when you insert the activity C, now you have in the detectable precedence set of activity C, you will include A and B. Okay, A and B will be part of the detectable precedence set of C. Okay, and so the while loop will insert them inside the theta tree. So you insert first the activity A and then the activity B inside the theta tree. So first you insert the activity A, then you insert the activity B, okay? And each time you do the insertion, you go from the leaf node of the corresponding activity and you update all the internal computations of the nodes up to the root. And then you have here the new possible early start time for the activity C. And what you see there is that at the root node, we have 10, okay? As we can see, we didn't insert the activity C itself, so this will have no impact, okay? Even if we remove it, that's still 10. And so 10 will be used to update the early start time of the activity C, and we will be able to push the start time of the activity C a little bit further, okay? And it will be 10 instead of 8. And so we have removed 2 values from the early start time of the activity C, exactly as we have seen on our example when we solved it initially to give us the intuition of what is the detectable precedence filtering rule. So that's a very efficient filtering algorithm for updating the early start time of the activities that can be executed in n log n if you use the theta trees, and if you consider the nested sets of the detectable precedence sets according to a very specific order, then you can compute them incrementally, taking advantage of the nested sets.